Hi, and welcome to another video. Today we're going to be talking about special triangles. This first one is called an equilateral triangle. Now, since it's equilateral, it obviously means that it has three sides of equal lengths. Let's call this one x. This one will thus be x, and this one will also thus be x. Now, recall that all the angles in a triangle add to 180, right? Now, if that's the case and all these sides are equal, then doesn't each angle have to be equal as well? In that case, each angle would have to be 180 divided by 3, which is equal to 60. So this will be 60 degrees, this will be 60 degrees, and this will also be 60 degrees. Now, how do we calculate the area of such a triangle? Well, it's pretty simple. In fact, we're just going to do base times height. Now, what base are we going to be doing? We're going to be doing the base from here to here, and the middle over here on the bottom, because when you think about it, if you go up all the way to the top, where there's a vertex, and then you pretend that this triangle over here on this side is actually getting moved over to here, then you essentially form a rectangle, a complete rectangle, like this, with this base b and this height h. Now obviously the area of a rectangle is equal to base times height. Therefore, you'll just do the base, this base over here, times this height over here. And that will give you this rectangle over here, which should be the area of the complete triangle. Another way to do this would be just to take this entire bottom area here, call this big B, and this h, still little h, and then say area equals 1/2 base times height, which is the usual form of the area equation for a triangle. Next we have the 30, 60, 90 right triangle. Let me move that over here. All right, let's examine that. So in the 30, 60, 90 right triangle, we obviously have an angle of 30 degrees, an angle of 90 degrees, a right angle, and an angle of 60 degrees. Now, obviously, these angles add up to 180. 90 plus 30 plus 60 is just 2 times 90 is just 180. And these side lengths are going to be as follows. Here we have x. Here we're going to say this diagonal is 2x. And here, this is going to be x times rad 3, or just rad 3 times x. Now, it's possible to remember these lengths by, just, like 1, 2, rad 3, like 1, 2, 3, but the 3 has a radical over it. Or you could just think, the two shortest sides are going to be the side lengths over, over here and here. And because 2 is larger than rad 3, 2 is going to have to be the hypotenuse. And then when it comes to which side is which, the x will be across from the smaller angle because it is less than x times the square root of 3. And this rad 3 will be across from the larger angle, which is 60. But it's really up to you as far as how you want to remember it. Now, this 30, 60, 90 right triangle gives us some important identities. So if we think about sine, cosine, and tangent, you know that sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. Now, you can remember this with the kind of mnemonic device so, ka, toa. But in case you haven't learned this already, this is just sine and then opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite, adjacent. Just those letters there. So yeah. Anyway, this opposite and hypotenuse for sine, if you're looking at sine of 30, it's going to give you this opposite x over your hypotenuse, which is 2x, and that will cancel. So let me just write that down. Sine 30 equals x over 2x. Now these x's cancel. These x's will cancel, and you'll get 1/2. Now if you're looking at say cosine of 30, just write that down. Cosine of 30 is going to be equal to this adjacent over hypotenuse. And that'll also cancel. So x rad 3 over 2x. Now these x's are going to cancel. You're just going to get rad 3 over 2. And finally for tangent of 30, you're going to get opposite over adjacent, which is going to give you x over x rad 3. Then these x's will cancel, 1 over rad 3. But usually we just rationalize this, so we multiply it by rad 3 over rad 3, and then that becomes rad 3 over 3. Now the same thing goes for 60. So sine 60, and I'm not going to write this out the same way I did last time. I'm just going to write sine 60 is going to be this this opposite over hypotenuse, which is going to be rad 3 over 2 after everything cancels. Cosine 60 is going to be this adjacent over hypotenuse, which is just going to be 1/2, and tangent 60 is going to be this opposite over adjacent, this rad 3 over 1, so it's just going to be rad 3. All right, so we've got that out of the way. Some important things to know. Now let's go on to the last important special kind of triangle that we have. Let's put it down there. All right, this is the 45, 45, 90 right triangle. This is obviously going to be the right angle right here for 90 degrees. This will be 45. This will be 45. Now, the angles, since these are both 45, we're going to have these sides be equal. It's actually an isosceles triangle. And then this diagonal here, we can actually just calculate using the Pythagorean theorem. A squared plus b squared equals c squared. Let's call one of these sides x. This side will then also be x. Then x squared plus x squared equals c squared. 2x squared equals c squared. X squared equals c squared over 2. Then, or wait, that's probably not the best way to do it. Yeah, so we're solving for c, right? So then c equals rad 2x squared equals x rad 2. So this is going to be x times rad 2. All right, then we have some more identities with sine and cosine. So sine of 45 will equal, well, let's think about it. Opposite over hypotenuse will yield 1 over rad 2. And then if we rationalize that like we did with the 1 over rad 3 for tangent earlier, we're going to get rad 2 over 2. Now for cosine 45, it's actually going to be the same thing. This adjacent over hypotenuse, we're looking at this angle here, but even if we did it the other way, it would be the same thing. Adjacent over hypotenuse will also be x over x rad 2, which is going to be 1 over rad 2, which is going to be equal to rad 2 over 2. So these are going to be equal for 45 degrees. Then tangent of 45 will equal, well, we've got x and x for our opposite and adjacent. Now x over x, anything over itself, is going to be equal to 1. And you can see this on the graph of tangent, actually. Right here, if we look at our tangent graph, then we can see that it goes a little bit like that. That's a horrible drawing of a tangent graph, but whatever. Anyway, so here is pi over 2, or 90 degrees. And here is pi. And here we're going to get whatever. And basically, over here or so, this is going to be half of pi over 2, which is going to be pi over 4. At pi over 4, right here, this should be equal to 1. And that can come in handy a lot, so I recommend you know it. This pi over 2 can also come in handy occasionally, just as a side note, because if we have, let's just draw another coordinate plane. If we have another coordinate plane like that, then sometimes they'll give you arctan, which looks kind of like this. And yeah, this is going to be arctan x. And as you can see over here, this is going to positive infinity. And then in this x direction, this is also going towards positive infinity. So then you know that it has to approach its asymptote at pi over 2, just because it's kind of the inverse of that, right? We're kind of swapping these things here. But yeah, so that can also come in handy. And then this will be at negative pi over 2. Anyway, that sums up the special right triangles thing. So hopefully you learned something today. Hopefully you enjoyed the video, and thank you for watching. See you next time.